perturbation theory we've looked at so far has been for systems with fixed perturbations. Nothing is changing in time. And we've been trying to evaluate new energy eigenstates for our perturbed system. Now, that's a very useful theory, but it does not help us with systems that are changing in time. A very common example of a time-varying perturbation might just be an oscillating perturbation, such as an oscillating electric or electromagnetic field, for example. This kind of situation would occur every time we shine a light beam at a material, for example, because we could start out by thinking of a light beam as just an oscillating electromagnetic field. Now, of course, if we have some time-varying perturbation in a system, we can still solve for what happens to the quantum mechanical state. We could just formally integrate the Schrödinger equation. But it would be quite useful to have a theory that might give us answers with less work than that, and we might reasonably expect that for relatively weak perturbations to the systems, we might be able to construct just such a theory. Time-dependent perturbation theory is indeed just such an approach. Like time-independent perturbation theory, it's a theory of successive approximations, but now for the time-dependent Schrödinger equation. This theory gives some quite simple results, and they're useful in a broad range of quantum mechanical problems. One very good example is the absorption of light by materials. The light fields that we typically shine at materials are relatively weak compared to the fields within the materials themselves. So this perturbation approach works well. And the simplest, that is, the lowest order perturbation theory, is usually good enough for that. Incidentally, even for quite strong laser beams shining at materials or atoms, perturbation theory still works well. Higher order time-dependent perturbation theory describes the resulting so-called nonlinear optical effects quite accurately. There we get effects such as second harmonic generation of light, which can turn an infrared invisible light beam into a visible one. And that's an effect used quite often in those green laser pointers, for example. Now that we're used to perturbation theories in general, it's actually relatively easy to introduce this time-dependent version. Note that in time-dependent perturbation theory, we are trying to calculate something rather different from the results we were looking for in time-independent perturbation theory. There we were trying to evaluate new versions of energy eigenstates, both in the energies of those perturbed states and in the wave functions. In time-dependent perturbation theory, we're trying to predict how some system is going to change in time. We'll therefore not have eigenstates or eigenenergies in our results. We will, however, still have wave functions, but now they will be changing in time. As before, we'll examine wave functions by expanding on some basis set, with the most convenient basis set typically being the energy eigenfunctions of the unperturbed problem. Those will still form a very convenient starting point, and we already know that at some point in time we can certainly expand any spatial function in them. What we'll be calculating now is how the expansion coefficients of these basis functions change in time. If we know that, then we can calculate the wave functions, or more generally, the quantum mechanical state, at some later time. If we know the quantum mechanical state as a function of time, then we can calculate any measurable quantity as a function of time. Hence, our algebra will now be focused on those expansion coefficients and how we can calculate them for small but time-varying perturbations. So now let's set up the necessary mathematics and the basic results.
For time-dependent problems, we can consider some time-dependent perturbation, so a perturbing Hamiltonian here that depends upon time. And we will consider that as an addition to an unperturbed Hamiltonian, h0 here. And we'll presume that that Hamiltonian, the unperturbed one, is not dependent on time. The total Hamiltonian then is simply the sum of these two, the unperturbed one plus our perturbing Hamiltonian that now, as we said, is explicitly going to depend upon time. To deal with a situation like this, well, we just use the time-dependent Schrödinger equation. And this is written, of course, in the usual form here for the time-dependent Schrödinger equation. And the ket here, the psi, capital Psi, is in general time-varying. Now, we presume that we could have solved the unperturbed problem, where the Hamiltonian was not depending upon time, and we could have deduced eigenfunctions and eigenvalues of that particular time-independent equation. So here was the classic time-independent equation here. And we can expand the solution, capital Psi, of the time-dependent Schrödinger equation as some superposition of these unperturbed energy eigenstates here that are a complete set for spatial functions. And rather deliberately here, we've put no time dependence inside this particular ket, and we've taken out the usual e to the minus I ent over h bar associated with the eigenstate psi n. We've put that explicitly here. And then additionally, because this function is going to vary in time in some possibly quite sophisticated way, we have also made our expansion coefficients dependent on time. Now, there's nothing odd about this here. We're saying that simply at any point in time, we could always expand the state capital Psi in these eigenfunctions of the time-independent equation, because that could express any function in space at a given time. And if we make the expansion coefficients depend upon time, then we can have a different solution at different points in time. And as I said, we've pulled this factor out here explicitly. So, as I said, we included this time-dependent factor explicitly in the expansion, leaving this time dependence here to deal only with additional changes that may be going on in the system. So we've taken this one out, so we're not having to deal with it within the an of t. Now we're going to substitute this expansion back into our time-dependent Schrödinger equation. And that will give us this larger expression here. And this an dot here is simply partial dan by dt. So we're using this notation with the dot, which is sometimes easy to miss, but that's the notation we're going to use. So here's the an dot up here that we got from this derivative. Now, this h naught times psi n, of course, just gives us en times psi n. And that means we've got an en times psi n on both sides in this term. So we've got h naught psi n, that will turn into en psi n. And we've got an en psi n in this side as well. And both of them are multiplied by an, so we can cancel those out. So then we get a slightly simpler equation, which looks like this. Now we can pre-multiply both sides of this equation that we've just derived by psi q, some specific energy eigenfunction. And that on the left will pull out just the one term from this summation here, the one corresponding to psi q. On the right, it does something a bit more interesting. We have psi q acting on the left here. Well, we're going to get a matrix element, psi q hp of t times psi n. And that's exactly what we have here. And now we still have to perform this summation over n, because in general, these matrix elements are not going to be 0 for specific q and any n. They might be 0, but they're not in general going to be 0. Now, so far, we've made no approximations at all. This statement here is merely a restatement of Schrödinger's time-dependent equation. It's still completely general. This equation and this equation are actually quite equivalent, provided we consider all possible q's here and have a set of these equations. Now we're going to consider a perturbation series. So we're going to introduce our expansion parameter, gamma, as before. We sometimes called it a housekeeping parameter. And we're going to write our perturbation not as just hp, but as before with the time-independent theory, we'll write it as gamma times hp. And as before, if you like, we can set the gamma equal to 1 at the end. In fact, it will usually cancel on both sides, so the issue doesn't arise. We can now express our expansion coefficients as a power series. So, as usual, we have these superscripts 0, 1, 2 up here, corresponding to the gamma to the power 0 term, the gamma to the power 1 term, and the gamma squared term, and so on. And we can substitute this expansion into the expression that we've derived that we know is just equivalent to the time-dependent Schrödinger equation. Note that we have gamma hp now instead of just hp. Now, in this expression, we can equate powers of gamma on both sides. That's the way we're going to construct our perturbation theory, just as we did before. And we'll have these expansions for AQ and AN. And the first thing we're going to do is equate terms in gamma to the power 0 on both sides of the equation. Well, this is very easy because on the right-hand side of the equation, for every term, there's at least a gamma to the power 1 in it. So on the right-hand side, there are no terms in gamma to the power 0. So the right-hand side is 0. On the left-hand side, we have IH bar and we have this factor here, but those are just numbers. In the power series expansion here for our time derivative, we are just going to have, therefore, the gamma to the power 0 term in here. We'll be looking at the time dependence of the 0th order coefficient on the left, but on the right we have 0, so therefore the time dependence of the 0th order coefficient is just, it doesn't depend on time. The derivative is just equal to 0. So the 0th order solution simply corresponds to the unperturbed solution. And this is the same behavior that we had in the time-independent perturbation theory before. And hence there is no change in the expansion coefficients in time to 0th order. That's no surprise. There's no perturbation involved when we're at 0th order. So with this power series here, and our expression with the gamma inside, for the first order term now, we're going to be equating terms in gamma to the power 1 on the left to terms in gamma to the power 1 on the right. Well, on the left, the term in gamma to the power 1 is going to involve the first order coefficient here, AN1. And on the right, since we have a gamma built in to start with, then the only term that's going to survive here in the expansion coefficients is going to be this 0th order term. So the first order term then becomes as follows. We take the IH bar and this complex exponential over to the other side. So our first order term here is just associated with the first order expansion coefficient correction. And on the right, we have the 0th order expansion coefficient and everything else that we see here. And we've cancelled the gammas. Now, incidentally, as we've done this, not only have we taken the IH bar over to the other side, we've also taken this complex exponential factor over to the other side and created a new notation for ourselves. And that notation is just to say that this omega Qn is equal to EQ minus En over h bar. And here we're trying to solve for what is the expansion coefficient, or the time dependence of the expansion coefficient, to first order for state Q. So instead of these two terms here, first of all, we've taken this one over to the right-hand side, and then we folded it into a new notation here, and omega Qn is just the difference in these energies divided by h bar. Now, note in this expression that we now have, we already know that all of these are just constants. They give us the starting state of the system at time t equals 0. We note now that if we know the starting state and the perturbing potential, and we know the unperturbed eigenvalues and eigenfunctions, so these psi n's here and the en's that are folded into this factor, we can integrate this equation in time. We're all set to do that now. We would now be able to obtain the first order time-dependent correction to the expansion coefficients, and hence actually we would know to first order the change in the wave function or the state of the system as a function of time. So then, formally, after integrating this equation, we know the new approximate expansion coefficients. They would be the unperturbed ones plus these first order corrections we would get from the integration in time of this equation. So we know the new wave function and can calculate the behavior of the system for this new wave function. We can, if we want, at this point proceed to higher order in time-dependent perturbation theory. We could equate powers of progressively higher order to give us equations like this, where we'd be looking at the p plus 1th order on the left, and we would find that it depended only on the pth order corrections on the right. So we can see that this time-dependent perturbation theory is also a method of successive approximations, just like the time-independent perturbation theory was. We can calculate each higher order correction from the preceding correction.
Just as for the time-independent perturbation theory, the time-dependent theory is often most useful for calculating some process to the lowest non-zero order. Fortunately, there's a broad range of interesting and useful problems that can be addressed even by this first-order time-dependent perturbation theory. These include ordinary linear optical processes and a wide range of interactions in materials, such as the scattering of electrons off crystal vibrations, so-called phonon scattering, and many other phenomena that influence the ordinary movement of electrons in materials to carry electrical current, for example. Higher order time-dependent perturbation theory is also quite useful, for example, in understanding nonlinear optical processes, as we mentioned earlier. So, first-order time-dependent perturbation theory gives the ordinary linear optical properties of materials. Higher-order time-dependent perturbation theory is used to calculate these processes such as second harmonic generation, two-photon absorption, intensity-dependent refractive index, and many other effects in nonlinear optics, processes that are actually seen quite routinely with the high intensities of modern lasers. Some are seen at quite low intensities in the long lengths of optical fibers, where, from an engineering point of view, they represent significant constraints on how well we can communicate over long distances.